this is just Mr. Tukin, and I want to go over how we can um, solve systems of linear inequalities. We're going to do this kind of in a step-by-step. When we talk about inequalities, they're a little different than equations. And so I've got an example of a linear equation on the board. And first off, let me apologize for my penmanship, but y equals negative 2x plus 3. Now, hopefully you remember things like slope-intercept form. A lot of times in your math classes, if you're getting to linear inequalities, that means you've already learned how to do equations. Well, what we learn in linear equations is that a graph of the line is in slope-intercept form involves a slope. Well, that's our 2, our negative 2, which is the same as saying negative 2 over 1. And remember, slope is going to tell us our rise over run. So we know that our slope of the line is going to be from one point to the next. We're going to go down 2 spots. And then because the 1 is positive, we're going to go right 1 spot. And then we also learn in slope-intercept form that positive 3, or this value over here, is our value of b, or what's something that represents the y-intercept. The y-intercept is always the point that crosses this y-axis. So we know the y-intercept is right here. And I probably should, let's change up the colors a little bit. Let's go red, if that hopefully shows up enough. All right, so we've got a point on the line, the equation of this line, which is at the y-intercept 0, 3 from this number. And then our slope told us we can go down 2, but then positive 1 says we go right 1. And you could do this a few times if you want. Since it's a linear equation, it's going to graph to make a straight line. And simply by connecting the dots, will we have our line. Now this could end up, let's get lucky. All right, so we've got an equation of a line. However, linear inequalities are going to do all of these same things. So you want to understand how to graph the slope and how to graph the y-intercept. But an inequality, the word inequality, says kind of like it's not exactly equal. It's not just equal to it. So when we talk about linear inequalities, we're involving a couple of symbols. We'll have a greater than symbol, we'll have a less than symbol. We can also have a greater than or equal to, and that's the line underneath. Or we can have a less than or equal to. So those are our choices. Now, for the sake of time, I'm going to try to select this thing. Let me go ahead and delete that line real quick. So we've got these key points, like I said, and we've got rid of that line. Well, an inequality means there are answers or values, and there's kind of more than one right answer. So let's go ahead, let me get rid of the slope explanation, and let's get rid of that equal sign. Let's go ahead and let's throw in, and I'll just keep it on red here, let's throw in greater than or equal to. Well, actually, let me backtrack. I'm not going to make it or equal to. I'm going to go ahead and I'm going to get rid of that. I'm just going to make it greater than. So we've got the inequality, y is greater than negative 2x plus 3. Well, the first thing we want to do is we want people to realize that it's not or equal to. It doesn't have any of that. So the first thing you would do is still graph the slope, or still graph the y-intercept, and still graph the slope. But once you do that, remember how we had that solid line before? Well, instead, we're going to replace that with a dashed line. All right, we're going to still connect the dots. We're still going to kind of go all the way through. We'll put a little arrow down like this, but we want to symbolize that there's no equal to. And we'll explain why that is in just a little bit. But then notice how it says greater. Well, there's more than one right answer here. And that's what this graph is going to symbolize. So we've got these dashed lines, but there's also going to be some shading involved. And the shading is going to represent ordered pairs or coordinates that if we plug them in, they would work in this inequality. And the example you'll usually see is 0, 0. 0, 0 is a nice one because, well, zeros are usually easy to work with. So remember, if we think of an ordered pair as 0, 0. Oh, by the way, I'm going to show this, but then I'm going to give you a little trick that you can use as well. But anyway, 0, 0. If we plug that in, we plug in the value of y as 0. And we plug in, oops, I'm getting a little ahead of myself here, -2, and we plug in 0 for x. The question becomes, does this work? Does this make, let me get rid of this little v looking thing up here. Does this inequality make a true statement? Does the left side end up being greater than the right side? Well, if we run the numbers here, notice we plugged in the point 0, 0, this location right here on the graph. -2 times 0 is, well, 0. Anything times 0 is still 0. And 0 plus 3 is +3. So when we plug in the point 0, 0, does it make a true statement? If you read this out loud, does it work? Or let me just do it. Is 0 greater than 3? Hopefully the answer at this point you're saying is no way. No, that's not a true statement. What that means is the answers on the other side, so here was 0, 0. If this doesn't work, then our shading, right? Our shading, it's not going to be over there. Instead, our shading needs to be on this side of it. So a lot of times you'll see kind of all of the answers, or let me go ahead and grab maybe a brush or something like that. No, we'll just grab this. And let's thicken it up. So anyway, all of this area over here is where our answers are. When I say our answers or our solutions, that means if you enter in any of these points, like let's say we go and we put a point right here, right? That's the point 2, +1. Well, 2, +1 is on that side of the shading. And what that means is if we come in here and instead of this 0, if we throw in 2, and if we throw in 1, this actually will end up making a true statement. So we know we've got 1. I'm going to write it over here. 1 is greater than -2 times 2. Well, that's -4. And we've got -4 plus 3. We still got this plus 3. Well, -4 plus 3 is -1. So again, when we get done, we say, does this make a true statement? Is 1 greater than -1? And the answer is yes. So if you can do that, it proves that this shading works. But remember, we checked originally. You can almost pick any point, but 0, 0 is usually easy to work with. And then if 0, 0 works, well, then you shade towards it. And if 0, 0 doesn't work, well, then you shade away from it. And the shading represents all of the points that would work. Now, I've got a little bit of a trick, but I'm even going to save that for another minute. I want to just go back to the dashed line stuff. Remember we had these dashed lines instead of a solid line. Why is that? Well, that actually represents that because this is just greater than and not greater than or equal to, if you have a dot like right here that is on the line, it actually does not work. It is not part of the solution. And the dashed line symbolizes that. It's telling you, hey, if you happen to find a point right on this line, it's not a part of the solution. However, if this had an or equal to with a little line underneath it, that means we'd use a solid line. Just like a linear equation, we'd use a solid line to connect the dots, and that symbolizes that it does work. And this point right here was what? This one right here, let's just prove what I was saying, that it's not going to work because this was just greater than. So that point is 2, -1. Well, one more time, if we plug in 2, -1, so the x is, the y is +2 here, well, think about it. The only thing that changes is this point over here is now negative, right? So the number is still +2, which means the right side's still going to end up equaling -1. But now we get a statement that says this. Is -1 greater than -1? And actually, no, that's incorrect. And again, that's why this is dashed, because this point doesn't actually work. Okay, so if we circle back, and I'm just going to keep going to this back button as fast as I can, lots of stuff going to disappear from your screen here. But if we go back here, and I mentioned there was a trick, right? Well, this symbol is greater than. And yes, you could check it with 0, 0. But a trick is if I was going to say greater, you could also think above. I want to shade above the line. So one little trick that you can use, now that you understand why we shade above it or away from 0, 0, is if it says greater, you can just go ahead and shade above. And all of those points are immediately the right answer. And if it says less, well then we're going to go ahead. If it says less, we're going to shade below the line. We're going to shade where it would be lower than the line. And again, those represent your solutions. So another thing we want to talk about here, as I go way back on this back, is horizontal equations of horizontal and vertical lines. So a lot of times you're going to have equations, and I'm going to get a new coordinate grid up here for us real quick. So similarly, we'll get equations of lines that are things like x equals, we'll say -3, and or we'll get equations of lines that are y equals, we'll say +4, okay? So these are equations, and just like we did before, you could end up with, okay, so what I did here was clear it out, and we've got a couple equations of horizontal and vertical lines. So these are actually equations of lines, things that we can graph. And again, hopefully you've already reviewed how to graph these or why they work. We're going to do a quick review of them. And similarly, like we did earlier, saw earlier, literally by just simply removing the equal sign, it's no longer an equation. And we could have one, let's use less than or equal to here. And we'll use we'll just do a greater than over here. So we have the same idea. So sometimes students want to know, well, how do I graph this? How does that work? Well, first off, just go to where x equals -3. So this is the x-axis. Here's -3, right? And let's go back to red. We'll use red for the x one. All right. Well, x is 3 here. In fact, that point, if we think about it, is -3, 0. The x value is, -3. But if we continue along that, technically, I mean, I could come up to this point, this point, this point, all forever and ever and ever. And I know the ordered pair changes, but the x value always stays the same. I come up here, it's 3, 3. I come up here, it's 3, 5. Notice how the x value is always the same. That's how we graph vertical lines, because the x value always stays the same. So that's an equation. That's how we get this line. But the same rules kind of apply. We have a less than or equal to. Because it's or equal to, we know immediately that we can create a solid line. And then since it's less than, which side of this line do you feel you would shade? Well, if it's an x value, the bigger x values are on this side. The less x values are on this side. This inequality says it is less than. So we would turn around and just start shading over this way. And all of our solutions, anything over here is an ordered pair that would work. If we go all the way back and we start talking about that y equals, or y is greater than for inequality, same idea. When we're doing a horizontal line, why is it horizontal? Well, go to where y is 4. That would be right here. When y is 4, there's also other points that y is 4. It's just the x value changes. But unlike the others, we would use a dashed line because this one doesn't say or equal to. And it says greater than. Where would you shade if it was greater than? Well, that's going to be above the line, right? So some pretty connect the issues or things we just did kind of still apply here. And this would be a graph of an inequality representing, well, it's a graph representing this inequality. So we've learned how to do like slope-intercept form, inequalities. Now we're talking about horizontal and vertical. Okay, so the final thing we have to focus on here when we're working on solving systems of linear inequalities. So similarly to systems of equations, remember we're building off of equations, we will run into maybe two equations, right? So I could have, let's go back to y equals, I think I had negative 2x plus 3. But let's also say I've got another equation which is y equals 3x minus 1. In math, everything builds. So what we would want to do to solve the system of equations graphically is we would simply graph the equation separately. So if we start with this one, again, we're in slope-intercept form. So we've got the y-intercept. And our slope says we go up 3 and right 1 because it's positive 3. So we're going to go up 3 and then right 1 because 3 is the same as saying 3 over 1. And if you want to do that a couple times, you can just to make sure that you have a nice straight line. But when we're done, we literally would just kind of, I have a feeling that's not going to be very good. So let's try it again. All right. So we've got an equation of a line. We then do it again for the other equation. So we kind of repeat that. Remember, we have inequalities we're dealing with, but I just want a quick review of this. So let's say I've got negative 2x plus 3, and that one, again, has a positive 3 up here. Then because of the slope, it's down 2 and right 1, and down 2 and right 1. When we're dealing with an equation or a system of equations, we want to remember that we are, yeah, I'm completely off there. So let's just get rid of that one. We are looking at the point of intersection. We are trying to find where the two lines will intersect, and that's going to be our solution. However, with a system of inequalities, remember how when we had a single inequality, it had many answers, many solutions. So let's go ahead and let's change this to an inequality. And they want us to show, using a graph, which is pretty much how you have to do it with inequalities, how, let's use greater than here. Let's come down here and we'll do blue with less than or equal to. So the first thing that's wrong with this graph, now that I've done that, is this other line is no longer good. It's going to need a dashed line because it's just greater than. So I'm changing this around to create kind of a little impromptu dashed line. Hope that makes sense. And it's symbolizing that there's no or equal to. Answers that are on this are no good. However, the other one, less than or equal to, so that's going to stay solid blue. Do you remember how we had the shading before? Right? We showed shading based on less than or greater than. So for this one, this blue one, it's a less than or equal to. So that would mean below the line, right? So you'll see oftentimes like colors, just all sorts of shading all over. And usually they'll use yellow and blue because yellow and blue make green, and they'll show like green. And that's kind of the hint here. But the idea is for an inequality, when you graph a system, oops, I need red because we're talking about this one. This one is greater than. So remember we talked about it shading above the line. So if we shade above, notice something. Where does the shading intersect? Well, the shading intersects in this whole area here. So that's where the solution to the system of inequalities is located. That's because the two all the answers in red in here, they work for this inequality. But also in this area, all the answers for blue also work. So they are the ordered pairs that would work if they're plugged into both inequalities. But because there's essentially like an infinite number of solutions, we have to do it graphically. We have to show that graph. So when you're looking at a system of inequalities, you're going to go ahead and look for where the shadings intersect, where they overlap. Okay, a lot to throw at you, but hopefully that's enough to kind of get you jump started and moving with systems of inequalities. Hope that helps. As always, reach out to your teacher for further